Question 22. So we have chemistry of crude oil. It's a mixture of many hydrocarbons of different length. Obviously, the longer the carbon chain, the stronger is the van der Waals because you have greater total number of electrons in the molecules, and therefore your boiling point will be different. And that's why you can separate them by using fractional distillation, something you will have come across from your previous O-level, GCSE level, or IGCSE level chemistry. What is the correct explanation for the difference in the boiling points of the three isomers with the same MR? So be very careful. They have the same MR because they are isomers. Compounds or molecules with the same molecular formula, different structural formula. Typically, they are referring to the structural isomers in this case here. So we cannot be thinking about total number of electrons, because if we just think about van der Waals, we know the primary factor for van der Waals depends on the total number of electrons in the molecule. But if you are isomer, you have the exact, if you are structural isomer, you have the exact same molecular formula. So you have the exact same number of electrons in the molecule. That can't be our primary factor here. And the difference, the reason in order to explain the different boiling point of isomer is down to the surface area. So when you have a straight chain, the straight chain can come closer together, and therefore this one will be stronger van der Waals as a result of a larger surface area. When you have a branch chain, the branch chain, imagine as a result of the branches, they can't get as close to each other, therefore you have a weaker van der Waals there as a result of the lower surface area. So the increased branching will increase the boiling point is actually wrong, because increasing branching would decrease the surface area. Your surface area would decrease, your van der Waals will get weaker, and in fact your boiling point will be lower when you have a branch chain, because the boiling point is going to be higher when the straight chain can get closer to each other as a result of a larger surface area. Increased branching reduces the strength of the intermolecular hydrogen bonding. Hydrogen bonding there is wrong because these are all alkane. Okay, we are not talking about polar molecule. These are non-polar hydrocarbon compound containing carbon and hydrogen only. Look at this thing here. Okay, increased branching reduces the strength, so that means it makes it weaker, which as I've just shown you, when you branch out you can't get as close to each other, and therefore if you are not as close to each other, your intermolecular force attraction is weaker. These are weaker van der Waals as a result of increased branching, and your surface area of the molecule decreases due to increased branching. Okay, so A is definitely wrong there because it says it's only dependent on the length of the carbon chain. In reality, it's dependent on the strength of van der Waals between the molecules from your structure and bonding topic. Question 23, we have compound Q. You have three double bonds in one single molecule. Which one will be ruptured? Okay, ruptured, or they can call it cleavage. Okay, this is the case study on the oxidation of alkene. This is a ketone. So this is a ketone, as you have a carbon and carbon, alkyl and alkyl next to a carbonyl. And then this is a carboxylic acid, as you could see the CO2H. When you're dealing with organic chemistry, the most important thing really is identify your functional group. This is a classic alkene chemistry there. So this is just looking at hot concentrated acidified CmNO4. This is a strong oxidizing agent. You can't oxidize the ketone or the carboxylic acid in this case anymore. You can only oxidize the alkene there. So compound Q contains that. Which bond will be ruptured? So it's not Y, the ketone is not further oxidized, it's just the X that's further oxidized by this concentrated acidified CmNO4. You will rupture it. This CH2, this will form CO2. This is a RCH double bond. It will give you a carboxylic acid fragment there upon the rupture of this alkene. How many lone pair of electrons are present in one molecule of Q? They are not asking for the oxidation product. They are asking for, in one molecule of this, how many lone pair of electrons are there? Well, we look at the oxygen, because that oxygen there will have two lone pair because it uses 2 out of 6 valence electrons for forming 2 covalent bonds. None of this carbon and hydrogen has any lone pair. Now this oxygen also has 2 lone pair there because they form a double covalent bond. This oxygen here doesn't form a double bond, but it forms a single bond to carbon, a single bond to hydrogen. It also has 2 lone pair. Altogether, the number of lone pair in one molecule of Q is 2, 4. Hang on, the number of lone pairs. So there's 1 lone pair, 2 lone pair, 3 lone pair, 4 lone pair, 5 lone pair, 6 lone pairs there. Okay, hopefully that makes sense. Question 24, we're looking for a compound that will undergo SN1 substitution reactions with aqueous and their OH. When you have you will form ROH as a result of RX reacting with OH minus like that, and then you kick out the X minus. This is a reaction called hydrolysis, which is why you are dealing with this using aqueous, that means in water, instead of ethanolic NaOH. Ethanolic NaOH or NaOH in ethanol will bring about elimination instead of your hydrolysis. Hydrolysis is the type of reaction. Type of reaction is as stated in introductory organic chemistry of the syllabus, but then the mechanism here could be SN1 or SN2, where you know SN1 is 2-step, and this will favor a tertiary halogenoalkane, where the halogen is bonded to the carbon. Bonded to the halogen is bonded to 3 other carbons, because you'll be forming via a carbocation intermediate. And you have been told in the syllabus specifically, stability of carbocation, tertiary is more stable than secondary, more stable than primary, inductive effect, stabilization of carbocations under the alkene bit of the syllabus. This one, SN2, is 1 step. It will favor the primary halogenoalkane, which doesn't want to form the stable carbocation. It just not so sterically encumbered or sterically hindered as a result of just having 2 hydrogens on the carbon bonded to the halogen. They can just do a 1-step reaction in order to bring about SN2 mechanism. So SN1 favor the tertiary halogenoalkane. We're looking for tertiary halogenoalkane. This is primary. The carbon bonded to the halogen. Is bonded to 1 carbon only. That's why it's primary halogenoalkane. They will favor SN2 instead of SN1. As for this one, this is called a vinyl halogenoalkane. It doesn't really have that category of primary or secondary or tertiary, because it is bonded to a carbon of an alkene. Not that it matters in this case, because you already got your answer to begin with, because your tertiary halogenoalkane is definitely going to be option C there. If you have a look at the carbon bonded to the halogen, the carbon bonded to the halogen is bonded to 1, 2, and 3. They will proceed via this tertiary carbocation, which is this thing here. The carbon with the positive charge is bonded to 1, 2, and 3 other carbon. This is quite stable compared to primary or secondary. This is the slow step. This is the first step in your SN1 mechanism in a 2-step reaction. That's why your reaction profile diagram will proceed via a double hump reaction profile diagram, because it will proceed via this thing called a tertiary carbocation intermediate. This is simply an energy profile diagram. So you have energy against the progress of reaction there. Question 25. If your starting material is iodoethane, so that is going to be CH3CH2I, which sequence of reaction will produce propanoic acid as your final product in good yield? This is a 3 times carbon, whereas when you have iodoethane, it's 2 times carbon. 2 times carbon to 3 times carbon, you need to add carbons. Immediately when you think about adding carbons, you need to think of nitrile. Okay, nitrile. Do you have HCN or do you have CN minus? When you are dealing with ketones or aldehyde, then you do nucleophilic addition of HCN. If you're dealing with halogenoalkane, HCN will not work on its own. Therefore, we'll be looking at CN minus like that, which means we need an ionic source of it. So this is your nucleophilic substitution. So this will be your 1 and 2. But now, because you have added 1 extra carbon, your nitrile is now the important carbon. That is called propant nitrile, because 3 carbon altogether. And then you can just do a hydrolysis. Hydrolysis of nitrile is as stated in the syllabus. Hydrolysis of the nitriles. Oops, I don't mean to do that. hydrolysis of the nitriles can be done by using dilute HCl and also reflux. Whereas that first bit there on the left hand side, the first step, can be done by using Na plus Cn minus, such as that. So it's an ionic source of the nitriles, and this will be done in ethanol as well as reflux. But what do we have? We have heat with HCN. HCN that is wrong. KCN is okay. KCN or NaCN, both of them are going to be ionic source of Cn minus. Therefore, it's much better. You don't deal with OH minus because if you put in the OH, you're just going to hydrolyze that. If I do NaOH aqueous, all I'm getting is I am just getting the ethanol. And if I oxidize the ethanol, what I get will be ethanoic acid, which is 2 carbon acid and not the 3 carbon acid as required by the question. So A and B are definitely out. D is the only correct and sensible option there. I have used HCl for my hydrolysis, but you could use any acid there and it will work for your hydrolysis, your acid hydrolysis of nitrile, where you break the triple bond totally in the presence of acid. That was done in water because any acid is dissolved in water there. It's called hydrolysis. Question 26, which compound cannot, so this is a negative kind of question, cannot be oxidized, but it reacts with sodium metal. If you react with sodium metal, you have a hydroxyl group. So hydroxyl group refers to OH. It could mean that you have alcohol. It could also mean it could be a carboxylic acid. But you cannot be oxidized. Cannot be oxidized means it could be a tertiary alcohol perhaps. It could also be aldehyde. It cannot be aldehyde because aldehyde can be further oxidized. It could be a ketone. It could also be a carboxylic acid. So all of them could not be oxidized any further. Okay, let's have a look at the options. So none of these look like ketone or carboxylic acid. So we are not really interested in looking at ketone or carboxylic acid. All we're interested really is tertiary alcohol, I guess. If you draw out the structure, I'm just going to draw the skeletal formula. The carbon with the OH, is bonded to 3 other carbons. This is a tertiary alcohol. Tertiary alcohol cannot be further oxidized, but it can react with sodium. So what happened then is it will give me the sodium ethoxide, and having done that, it will give me a hydrogen gas, which I need to balance it off with just a half because that is a molecule. So that thing there is a balance equation for the reaction between this alcohol and sodium. A is in fact our answer there. B is ketone. Actually, I was wrong to dismiss ketone, but B is actually ketone. If you see the C double bond O there, there's a ketone, but there is no hydroxyl. So B cannot be our answer because it doesn't react with sodium metal. C there, that is a primary alcohol because the carbon bonded to the OH is bonded to one of the carbon. You can oxidize it using acidified Cr2O72-. This thing here in D, this is a carbon with the OH, is bonded to 1 carbon and 2 carbons. This is a secondary alcohol. You also can be oxidized to a ketone there. So C and D cannot be the answer. Question 27, butane-2-ol can be made by reducing X with hydrogen and nickel. This is your catalytic reduction. So I call it reduction because in fact you are adding hydrogen and hydrogen, so the carbons will have gained hydrogen. Okay, so butane-2-ol is an alcohol. You can be dehydrated to form Y and Z. What do we have? So if we look at butane-2-ol, so let's have a look at butane-2-ol. 1, 2, 3, and 4. So there's your OH there. If I imagine this, if this come from aldehyde or ketones, so what could have been reduced to give me that? So I would have gained this H. I would have gained the H on this carbon from 4 bond, 1, 2, and 3. So that means there must be 1 hydrogen there, which is not shown. So perhaps you can hopefully see that it must be a ketone and not an aldehyde, because if it is an aldehyde, you will have started from primary alcohol, where you will have ended up with primary alcohol, where if you have the aldehyde, let me just show you. If you have the aldehyde, if you add in the H and the H, so that means the H will add there and the H will add there, you will end up with like that, where you have 1 H added on the oxygen and 1 hydrogen added there. But you have added a H and a H one to the oxygen and one to this carbon there. This is addition of hydrogen across a double bond, but actually this is actually reduction of this carbonyl because the carbons they gain hydrogen. Okay, so hopefully that makes sense to you. So it means it cannot be an aldehyde. So A and B is definitely wrong. In terms of the dehydrated product, so I know that aldehyde cannot be the answer. So in terms of the dehydrated product, I could have my hydrogen there. So I could imagine removing that. So the pink color route will give me that. And if I have a green color there, a green color route would be this way. It can remove from the other hydrogens on the other carbon. This is a CH3, this is a CH2. They are different. That's why I'm showing you the two different products that you could get. And of course, when you have this particular product here, this is the trans isomer, where you could also have the geometric isomer, where it's cis. These two groups are on the same side. They are prevented from rotating about the double bond freely because this is a pi bond. It prevents or it restricts rotations, free rotations. Therefore, these two are isomers different in the three-dimensional arrangement of the atoms. So cis-trans isomerism, or what you call geometric isomerism, it is shown by can be dehydrated to form Y and Z, which are structural isomer. So I guess only one out of Y and Z, because if one of these is Y, one of these is Z, they are structural isomer of each other. Y and Z are structural isomers of each other. In fact, they are what you call position isomer, because that is 1, 2, 3, 4 like that. So that is your but 1 int. Okay, whereas on the right hand side, what you have is but 2 int, but you have a trans but 2 int, or you could have cis but 2 int. Where am I? I think I've made a mistake of going to the previous page. Let me just go back to our page here. So this is cis but 2 int there, trans but 2 int. But what the difference between Y and Z, which are structural isomers of each other. So cis and trans is not shown by both Y and Z, but by only one of Y and Z, which means D must be the only possible answer. 28. So we have tolerance reagent. Tolerance reagents will be the use for testing aldehyde. So aldehyde will give you positive, ketone will give you negative. This is your CHO. If you write the structural formula, you write this as such. This is your aldehyde. The name is called ethanol. Okay, ethanol. This is a ketone, so CH3, C double bond O, CH3. This is propanol. This is an alcohol. The carbon with the OH, as I've highlighted here, is bonded to two other carbons. This is a secondary alcohol. Which one will be a positive result, meaning to say your tolerance reagent, which is silver +1 in the tolerance, will go to form the silver mirror, which is silver 0. So this is your silver mirror, all your silver precipitate in this case. So only aldehyde will do that. So aldehyde, which is P, Q and R will not do that. So only P is the answer there. 29. So sorbitol is a naturally occurring compound, so it's a sweetener. How many chiral center? Chiral center refer to a carbon bonded to 4 different other carbon. This is a CH2. When you have CH2, this carbon cannot be chiral. This is a CH2. This carbon cannot be chiral. Okay. In terms of symmetry, 1, 2, 3, 4, 5, 6. So we can see that there is a symmetry there. So there's a symmetry there. If I am looking at this carbon here, this carbon is chiral because hydrogen, OH, 1 carbon, many carbon. Okay. If I'm looking at this next one, so let me see, is it chiral? Is it not chiral? It is going to be chiral because this thing here has 2 carbon. This thing here has 3 carbons. You always focus on where are you. You're at the green carbon here. Hydrogen and OHs are different. 2 carbon, 3 carbon, they are different like that. Okay. If you go on to the next one, the one on top there, so as you could see, as I pointed out just now, this one is a mirror plane. So when you go to this carbon here, I go to this carbon here, what do we have? This carbon here will have a chiral carbon as well because 1, 2, 3 carbons and 1 and 2 carbon, they are different. And last but not least, you can have the other last chiral carbon, the brown color one. 1 carbon there, more than 1 carbon there. So altogether, what you have is you have 1, 2, 3, and 4 potential chiral center there. Okay. Question 30, which compound produces butane-2-ol and also ethanoic acid on hydrolysis? This is an alcohol, and then the other one is a carboxylic acid. So you are doing hydrolysis of ester. Acid hydrolysis of ester will give you the acid. If you do base hydrolysis of esters, the carboxylic acid will not be obtained because they will react with the base to give you the salt. So in order to do this kind of question, draw and see. Okay, so I'm going to draw out and see it for myself. If you follow this, CH3, CO2, CH, because carbon from 4 bonds, 1, 2, 3, there is one hydrogen there, CH3 twice. If I hydrolyze this, I would hydrolyze there. So that means I will get these 2 carbon acid. So 2 carbon acid is okay. But this thing here, I will get a propane 2-ol, only 3 carbon. If you look at that, 1, 2, and 3, propane 2-ol is not butane 2-ol. A is wrong. If I look at B, draw and see for yourself. Draw and see for yourself. So what I'm going to do is that CH, CH3, CH2, CH3. Always check CH3, CO2. You see I made a mistake. I haven't included the ester there. CO2, CH, CH3, CH2, CH3. Let's do this again. CH3, CO2, CH, there's one hydrogen, CH3 branch, CH2, CH3. So if I hydrolyze this ester, I'm going to get carboxylic acid because I am doing acid hydrolysis. If I do base hydrolysis with sodium hydroxide, I will get the sodium ethanoate. Anyway, I want the lowest number for my OH, and guess what? This is my 4 carbon alcohol. I have an OH at position 2, that's butane-2-ol. This is 2 carbon acid, ethanoic acid, so B must be the answer there. Okay, out of interest, I mean, I'm doing a tutorial, so I should really show you where things are going. So CH3, CH, CH3, C double bond or CH2, CH3. Double check this with this formula for CH3, CH, 1 hydrogen, carbon from 4 bond, 1, 2, 3, there's 1 hydrogen. CH3 is branch in a bracket, CO2, CH2, CH3. So you're going to break it up like that. You will not get ethanoic acid. You will get more than 3 carbons in the carboxylic acid, so that would be wrong. This is a 2 carbon alcohol. It will not be 4 carbon alcohol, so C is also wrong as well. You can do the same for D if you draw it out and see for yourself. I'm just going to quickly draw this branch and then CH2, CH3. CH3, CH2, CO2, CH, carbon from 4 bond. There's a CH3 branch, CH2, CH3. You can then, break it up there. And then you will get 1, 2, and 3. You will get a propanoic acid. And then on this side, you will get OH like that. You will get 1, 2, 3, and 4. So you do indicate butane-2-ol, but you get propanoic acid instead of ethanoic acid for option D there. In this section B type of questions, you are given a series of statements of which these are the only possible options, the combination of which are correct. So we always go for option number 2 first, and when option number 2 is wrong, that means D is the only possible answer. When option number 2 is correct, we check for number 1, and if number 1 is wrong, that means only C must be correct. And then if number 1 is correct, then we go for number 3. If number 3 is wrong, that means B is correct. If number 3 is correct, then A is going to be the only possible option. So these are the possible logics in terms of the combination of the statements. As far as I'm aware, the new syllabus coming out in the year 2022 onwards is already specified that this section B has been scrapped off, but it does not mean that they cannot ask you questions such as this section B type of question. It just means that there wouldn't be exactly 10 questions, or it could be exactly 10 questions. It could be more, it could be less. Okay? In this question 31, we have a couple of statements about orbitals. So you need to be very clear about what is shell, what is subshell, and what are orbitals. So in terms of, let's say, n equal to 3, I will have the subshell of S and the P and the D. For the S, I will have 1 orbital. For the P, I will have 3 orbitals. For the D, I'll have 5 orbitals because I will draw 5 lines or 5 boxes in which I can fill electrons in. That's why there are 10 elements across the D block transition metals. There are 6 elements across the P block right hand side of the periodic table, and there are 2 elements filling in this one box, or 2 electrons in one of these orbital for the S block elements group 1 and group 2. So in terms of statement number 2, the third energy levels, n equal to 3, it does have 3 subshells. As you could see, as that's what I had done. The 3s, the 3p, and the 3d, 3 subshells. The 9 orbitals, 1 plus 3 plus 5, that give you 9 orbitals altogether. So these are all about terminologies and whether you are well versed in the terminology as stated in the AS syllabus or not. Statement number 1, the 1s and the 2s orbitals have the same energy. This is a misconception. They do not have the same energy. In fact, they have different energy. If you draw 1s, they'll be at the bottom, and then 2s will be above 1s. They are not having the same energy. However, the 3 orbitals of the 2p, they are what you call degenerate. They have the same energy, but there's still higher energy than the 2s there. So 1 is definitely wrong, 2 is correct, 1 is wrong. Definitely we are looking at statement number C there. You can have a look at statement number 3. 3D subshell has 5 orbitals that have the same energy. So as I mentioned there, the 3D orbitals has 5 orbitals. You would draw the 5 boxes where you can fill the electrons like that, and then you can completely fill them up by pairing them up after you have the parallel spins in the maximum manner. You pair them up until you get 10 electrons fully filled, 10 elements across the D block series there. So question number 31, the answer must be C there.